So I'm going to go through some slides here and show you some pictures. So here we can see this flat plate that's oriented in the direction of flow. So the flow is mostly parallel to the plate. You can see these streamlines going around it. And then if it's oriented normal to the flow, you can see how the how things look quite a bit different then. And you can see this big area in back of the plate where there's no streamlines, and that's going to have very low pressure back there. And then you can also see on this cylinder down below the flow going around it. And I believe in lecture on Monday, you heard from Dr. Foster about flow separation, which you can see is occurring there and there. The flow is separating from the walls, and you're getting this low pressure area in back. Here we have basically a coefficient of drag and how it's dependent on shape for a circular, for a sort of an ellipse or cylindrical-like object. Here's what we showed before from the notes. You can see the flow separation again occurring in this upper right diagram here. For a more streamlined body, however, where you see this tail oriented back here, we can delay flow separation from the front of the body all the way around to back here. And by doing that, we are minimizing that difference in pressure between the front of the object and the back of the object, which results in a lower drag force. Here you can see again, this is a wing, and as it's orienting at different angles of attack is what they're called. There's 5 degrees in the upper left versus 15 degrees in the lower left and 30 degrees on the right. At some point, you get to this condition where you see flow separation occurring at the top and the bottom. And now this is what's called the stall condition for an aircraft that's in flight. You don't want to have a stall condition like this where you have flow separation over the entire top of the airfoil. So how does drag coefficient depend on Reynolds number? There is a dependence on that. For what we call creeping flow, which I believe you talked about on Monday, this is where Reynolds number is much greater than 1, extremely slow flow. It turns out that the coefficient of drag doesn't have a very large dependence on Reynolds number. If you look at these 3 objects, the sphere, the hemisphere, and the circular disc, 24 over the Reynolds number, 22.2, and 20.4, not a big difference. A little bit different for the circular disc, parallel to the flow, but in general, not a huge dependence on that. But here we can see a disc oriented to a flow at normal Reynolds numbers that you would see, and you can see how the drag coefficient can vary by almost a factor of 2 depending on the Reynolds number. Generally speaking, for many objects, the higher the Reynolds number, the lower the drag coefficient gets. These are the tables from your book that will show you the drag coefficients for various objects for when you're doing homework problems. And on exams and so forth, we'd provide these kinds of tables. So this is one page, and then this is the second page. This diagram just shows how the overall drag coefficient for a whole composite body, like a car, has decreased over time as you've gone from a car that isn't very streamlined up here to more streamlined versions and cars over here. The overall drag coefficient has gone down. When we go to the Daimler wind tunnel, you'll hear them talking a lot about, basically what they're trying to do in that wind tunnel is lower the drag coefficient, which lowers the amount of fuel you have to burn in order to overcome drag on the road. This is just the back of a U-Haul van showing how they enhanced aerodynamics, and you can see things like mirrors, the forward bumper, the side skirts, rounded corners to basically increase fuel economy. And then flow over a flat plate, I'm going to go back to the notes I've prepared. Um, so if you can hang tight here, I'm going to pause the video and